Let's try a more concrete example. Let's say we have the integral from 2 to 6 of 1/2 x minus 2 dx. What is our curve? Our curve is the function y equals 1/2 x minus 2, and we go from x equals 2 to x equals 6. What does this curve look like? We have a y-intercept of -2, and we go up 1 over 2. Up 1 over 2, up 1 over 2, up 1 over 2. Have we reached our endpoint yet? We want to go from 2, x equals 2, up to 1, 2, 3, 4, 5, 6. Yes, x equals 6. So our curve is a straight line, and this is almost too easy because, again, this area exactly balances out with that area. So the answer is 0. From 2 to 6, 1/2 x minus 2 dx is 0. If we had just gone from 1, 2, 3, 4 to 6 of 1/2 x minus 2 dx, we would have had just this area. Just this area, which is a triangle, base of 2, height of 1, 1/2, 2 times 1 is 1. So not terribly exciting, but you get the idea. This part tells you what your function is. This, you start at the bottom, x equals 2. You end at the top, x equals 6. Why are they x's? This thing tells you the x's. And this is as much of a decoration as that squiggle is. Now at this point, you should be able to calculate areas under curves for anything where the area under the curve is understandable. What does that mean? That means straight horizontal lines that break the area under the curve into nice rectangles, or straight lines that break things into trapezoids and triangles, or I could even give you something like a semicircle. And if I said, what is the integral, let's call this g of x, y equals g of x. If I said, what is the integral from 0 to 2 of g of x dx, you would say, is that a perfect circle? And I'd say, pretend it is. I tried very hard to draw a perfect circle. And then you'd say, well, it's the area between the curve g of x and the x-axis from 0 to 2. We're talking about a quarter of a circle. A quarter of a circle that has pi r squared. What is r? R is 2. So 1 quarter of pi times 2 squared, which is 4, which is exactly pi. Hey, I know that one. 3.14, etc. units, whatever these are. Is that 2 inches? Then a little bit more than 3 square inches. Is that miles? Oh, a little bit more than 3 square miles. Now, of course, there are going to be lots of things out there that are hard. For example, if I said the integral from -2 to 1 of x times x plus 2 over x minus 2 times x minus 3 dx, you would say, oh, lordy, lordy, lordy. You'd probably break out a flag diagram, maybe. Flag at 0, flag at -2, flag at 2, and at 3. Oh, I messed this one up. I totally messed this one up. Ah, well, undefined at 2 and 3. We have zeros at -2 and -2 and 0. It is what? Positive, negative, positive, negative, positive. So our curve looks like 1, 2, 3. We have vertical asymptotes at 2 and 3. We have zeros at -2 and 0. the curve is somehow above the x-axis beforehand, what kind of asymptote do we have? We have the asymptote of y equals 1, because when you multiply this out, you get x squared up top, x squared down below. It's going to level out to 1. So my function is going to be above, coming down from a horizontal asymptote. It will dip below the x-axis briefly, and then it will go shooting off to a vertical asymptote. Between these two asymptotes, it's negative for a little bit, and then afterward it's positive, and it lowers down. Well, that's quite a lovely function. But, lordy, what is this function? We start at -2, and we go to 1, and this counts as negative, and this counts as positive. Which one is bigger? The way I drew it, it's more negative than positive, so it's some negative number. It very well might be that I drew it poorly and it goes shooting off faster and it's more positive than negative. So be it. But this is what it means. If you want to do a more abstract problem, we could talk about something like, suppose you're given information like the integral from 0 to 8 of h of x is 7, and the integral from 5 to 8 of h of x is 3, and the integral from 8 to 10 of h of x dx, I forgot that dx isn't all of them, is -10. dx, shame on me, I'm going to yell at you guys if you forget your dx's. And I say, what is the integral from 5 to 10 of h of x dx? And we don't even have a picture, but we have all sorts of information. We know that if you go from 0 up to 8, you get 7, and from 5 up to 8, you get 3. That is to say that your function from 0 up to 5, and then from 5 up to 8, somehow the area in here is 3, and the area all the way up to, from 0 to 8 is 7, so there must be an area of 4 in there. Some sort of curve like this. And yet when we go from 8 to 10, it's negative. So we have some sort of huge -10 there. But you don't even need to draw the picture. You need to just say, well, wait a second. From 5 to 10, well, if you add, let's see, if you take this and subtract this, you get the integral from 5 to 8 of h of x dx is 4. No. We already had 5. Oh, this is totally unnecessary. Ridiculously unnecessary. So what? It's a red herring problem. That doesn't mean anything. All you have to do is you go from 5 to 8, and then you extend it from 8 to 10. 3 minus 10. From 5 to 10, it's 3 minus 10, -7. It's more negative than positive. Now, we don't know what the curve looks like, and that's a really sad-looking curve, but you can figure out problems like this. Abstractly, you don't even need the picture. You could have just said, well, what other information do we know? We know that if you go from 0 to 5 of h of x dx, from 0 to 5 has to be 4. Because all from 0 up to 8 is 7, from 5 up to 8 is 3. The rest must be 4. What else do we have here? From 0 to 10, from 0 to 10, h of x dx, that's just what, 0 to 8. That's the area from 0 to 8, h of x dx, plus from 8 to 10, h of x dx, and that was what? 7 minus 10, which is -3.